Good day, everyone. We are Group 10. Today we will discuss hydrogen and fuel cells, its significance, methods of production, types, utilization, application, advantages, and disadvantages. Before we start with the discussion, let me give you a short overview on hydrogen and fuel cells. One major problem with renewable energy sources is inability to store the produced energy in a viable manner. This is not a problem with biomass since the fuels produced from biomass such as ethanol and biodiesel can be stored and used anytime. However, the electricity produced from solar systems, hydroelectric dams, geothermal, power plants, and wind turbines cannot be stored for later use. Batteries are not a viable option in today's technology due to their limited capacity. One possible solution to this problem is production of hydrogen from renewable electricity by the electrolysis of water. Once produced, hydrogen can be stored and used anytime. Hydrogen is a colorless, odorless, nonmetallic, tasteless, high flammable diatomic gas with the molecular formula H subscript 2. It is also the lightest element with a molecular mass of 2.016 kg per kmol. Hydrogen is a fuel with a higher heating value of 141,800 kilojoules per kilogram and a lower heating value of 120,000 kilojoules per kilogram. Note, however, that hydrogen is not an energy source like coal, oil, and natural gas since there are no hydrogen reserves in the Earth. Although hydrogen is the most plentiful element in the universe, making up about three-quarters of all matter, free hydrogen is scarce. Hydrogen must be produced from other fuels such as natural gas or from water through electrolysis by consuming electricity. Therefore, hydrogen should be called an energy carrier rather than an energy source. The following are the methods of how we can produce hydrogen. First is steam reforming, followed by water gas shift, and lastly, the water electrolysis. The steam reforming is a much cheaper method of producing hydrogen compared with the water electrolysis. However, using a fossil fuel source for producing hydrogen is not a sustainable method. Most hydrogen is produced from natural gas through process of steam reforming. The steam the water gas shift is a highly valuable industrial reaction that is used in the manufacture of ammonia, hydrocarbons, methanol, and hydrogen. The combination of two reactions is given by this equation. Therefore, for 1 kmol, about 16 kilograms of methane used in this reaction, 4 kilomole, about 8 kilograms of hydrogen is produced. The steam reforming process is endothermic requiring 206,000 kilojoules per kmol of hydrogen of energy input while the water gas shift reaction is exothermic with an energy output of 41,000 kilojoule per kmol of hydrogen. The net result is 165,000 kilojoule per kmol hydrogen energy input. This is equivalent to 81,850 kilojoules or 22.73 kilowatts-hour energy input per kilogram of hydrogen produced. Hydrogen is also produced from oil, coal, and biomass. The steam reforming is a much cheaper method of producing hydrogen compared with the water electrolysis. However, using a fossil fuel source or natural gas for producing hydrogen is not a sustainable path. We are primarily interested in water electrolysis since it allows the use of electricity generated from renewable energies. Nuclear electricity can also be used. This reaction produces 1 kilomole hydrogen about 2 kg and zero point 0.5 kilomole of oxygen about 16 kg. When 1 kmol, about 18 kg of water is used. The minimum work required for this endothermic reaction is given by the Gibbs function of water at 25 degrees Celsius, which is equal to 237,180 kilojoules per kmol of liquid water entering the reaction. This is equivalent to 117,650 kilojoules per kilogram of hydrogen produced by the reaction. Note that this is very close to the lower heating value of hydrogen, 120,000 kilojoules per kilogram. An actual electrolyzer involves irreversibilities, and the actual electricity consumption will be greater than this minimum value. The efficiency of a typical electrolyzer is about 80%. Therefore, there is no thermodynamic advantage of producing hydrogen through water electrolysis by consuming electricity. The reason is that we cannot store renewable electricity effectively by other methods.
For the production, storage, and utilization of hydrogen. As mentioned earlier, hydrogen is to be produced by a electrolysis process. Once produced, hydrogen can be used as a fuel for an internal combustion engine. It can be burned just like gasoline, or a fuel cell can be used to convert energy of hydrogen into electricity. One of the greatest advantages of hydrogen is that the exhaust of a hydrogen engine does not contain carbon monoxide, sulfur, hydrocarbon, or carbon dioxide emissions. The exhaust of a fuel cell using hydrogen is water. Hydrogen is the primary fuel to power fuel cells. Fuel cell powered cars, bikes, stationary and portable generators, electronic devices such as computers and cell phones can all use hydrogen as the fuel. A mobile phone powered by a fuel cell using hydrogen as the fuel cell as the fuel can have several months of battery life compared to just several days with the current batteries. Hydrogen can be used in a variety of applications, including electricity generation plants and various industrial, commercial, and residential use. As seen in the figure, uh, to produce a hydrogen, the inputs are water and electricity. Such electricity are from renewable resources such as solar, wind, hydro, geothermal, biomass, and wave. Hydrogen can be combusted with air with concentrations ranging from 4 to 75%. Due to this wide flammability range, hydrogen must be handled with care. In the fuel cell, the hydrogen flow to the stack can be shut off in case of fire. The high diffusivity of the hydrogen and fast bending of storage tanks can help reduce potential for spreading of flame. Production, storage, and transportation, refueling, and use of hydrogen present a number of technical, economical, and practical problems, and a large number of research are underway to tackle these problems. For example, the storage of hydrogen in liquid form requires very low temperatures, which are expensive to achieve and maintain. Its storage in gas form at high pressure, on the other hand, involves low density, and a full tank will have a low range of mileage. Extensive tests indicate that pressures at high as 70 megapascal can safely be used for compressed hydrogen storage in commercial vehicles. Fuel cells. Fuels like natural gas, primarily methane, coal, and oil, are commonly burned to produce thermal energy at high temperatures for use in the heat engines. For example, when methane at 25 degrees Celsius is burned with 50% excess air at 25 degrees Celsius adiabatically, the products will be at 1789 Kelvin. In other words, the work potential of the hot combustion gases is about 65% of the work potential of the reactants. It seems that when methane is burned, 35% of the work potential is lost before we even start using the thermal energy. A fuel cell uses the chemical energy of hydrogen or other fuels to cleanly and efficiently produce electricity. If hydrogen is the if hydrogen is the fuel, the only products are electricity, water, and heat. Fuel cells are unique in terms of the variety of their potential applications. They can use a wide range of fuels and feedstocks and can provide power for systems as large as a utility power station and as small as a laptop computer. Fuel cells can be used in a wide range of applications, providing power for applications across multiple sectors, including transportation, industrial, commercial, residential buildings, and long-term energy storage for the grid in reversible systems. Fuel cells have several benefits over conventional combustion-based technologies currently used in many power plants and vehicles. Fuel cells can operate at higher efficiencies than combustion engine and can convert the chemical energy in the fuel directly to the electrical energy with efficiency capable of exceeding 60%. Fuel cells have lower or zero emissions compared to combustion engines. Hydrogen fuel cells emit only water, addressing critical climate challenge as there are no carbon dioxide emissions. There are also no air pollutants that create smog and cause health problems at the point of operation. Fuel cells are quiet during operation as they have few moving parts. A, a fuel cell functions like a battery, except that it produces its own electricity by combining a fuel with oxygen in a cell electrochemically without combustion and discards the waste as heat. A fuel cell consists of two electrodes separated by an electrolyte such as a solid oxide, phosphoric acid, or molten carbonate. The electric power generated by a single fuel cell is usually too small to be of any practical use. Therefore, fuel cells are usually stuck in a practical applications. This modularity gives the fuel cells considerable flexibility in applications. The same design can be used to generate a small amount of power for a remote switching station or a large amount of power to supply electricity to an entire town. Therefore, fuel cells are termed the microchip of the energy industry. As seen as the figure, the operation of a hydrogen-oxygen fuel cell is illustrated. Hydrogen is ionized at the surface of the anode, and hydrogen ions flow through the electrolyte to the cathode. There is a potential difference between the anode and the cathode, and free electron flows from the anode to the cathode through an external circuit, such as a motor or a generator. Hydrogen ions combine with oxygen and free electrons at the surface of the cathode, forming water. Therefore, the fuel cell operates like an electrolysis system working in reverse. In steady operation, hydrogen and oxygen continuously enter the cell as reactants and water leave as the product. Therefore, the exhaust of the fuel cell is drinkable quality water. The, f- the fuel cell was invented by Groves in 1839, but it did not receive serious attention until the 1960s, when they were used to produce electricity and water for the Gemini and Apollo spacecraft during their missions to the moon. Today, they are used for the same purposes in the same shuttle mission. Despite the irreversible effects such as internal resistance to electron flow, fuel cells have a great potential for much higher conversion efficiencies. Currently, fuel cells are available commercially, but they are not competitive only in some niche markets because of their higher cost. Fuel cells produce high quality electric power efficiently and quietly while generating low emissions using a variety of fuels such as hydrogen, natural gas, propane, and biogas. A single fuel cell produces between zero point 0.5 and zero point 0.9 volts of electricity. For usable voltage and reasonable power outputs, fuel cells are combined into stacks. Recently, many fuel cells have been installed to generate electricity. For example, a remote police station in Central Park in New York City is powered by a 200 kilowatt phosphoric acid fuel cell that has the efficiency of 40% with negligible emissions. Hybrid power systems that combine high temperature fuel cell and gas turbines have have the potential for very high efficiency on converting natural gas to electricity. The primary objective of a fuel cell is to generate electricity, but heat is also produced. This heat can be used for space and water heating for buildings. The efficiency of a combined heat and power plant that operates on a fuel cell can reach a utilization efficiency of 90%. Some car manufacturers are planning to produce cars powered by fuel cell engines, thus nearly doubling the efficiency from about 30% for the gasoline engines to up to 60% for fuel cells. A recent technology of fuel cells involves dual operation of the system. The fuel cell is normally used to produce electricity. However, the operation can be reversed so that the fuel cell produces hydrogen and oxygen by consuming electricity. This electricity should come from the excess electricity produced from the renewable energy sources such as solar or wind system. The hydrogen produced will be used when electricity demand is high. The fuel cells that operate on this principle are called regenerative fuel cell or reversible fuel cell. Fuel cells are usually classified according to the electrolyte used. The main types are to be briefly described based on Hodge and Department of Energy. Types of hydrogen fuel cells. Proton exchange membrane fuel cell or PEMFC. It is also called polymer electrolyte membrane fuel cell. This fuel cell contains a thin plastic polymer membrane which is coated by platinum particles acting as the electrolyte. The operating temperatures are low, and important advantage of PEMFC is its small size for a given power output. The power output can be varied easily depending on the demand, which makes this fuel cell best candidates for automobiles. Stationary power generation is another good application for PEMFC. Second, direct methanol fuel cell. This fuel cell uses a polymer membrane as the electrolyte. It uses the methanol directly in the cell. These fuel cells can be used for powering a laptop computers and battery recharges such as in cell phones. Alkaline fuel cell or AFC. This type of fuel cell uses potassium hydroxide or an alkaline membrane as the electrolyte. They operate between 20 and 250 degrees Celsius with efficiencies of up to 60% at low temperatures. Alkaline fuel cells require pure hydrogen as the fuel, which is expensive. As a result, their application is mostly limited to space applications to produce electricity and water. Portable water production is a new application for alkaline fuel cells. Phosphoric acid fuel cell or PAFC. Phosphoric acid is used as the electrolyte while platinum is used as the catalyst, which is negative. Porous carbon electrodes are used in both cathode and anode. The operating temperatures are about 200 degrees Celsius. Their current thermal efficiencies are between 35 and 45%. PAFCs are mostly used in stationary power generation with power outputs of greater than 400 kilowatt. Ideal applications include hotels, stores, hospitals, and other buildings for which rejected heat from the fuel cell can also be used for useful heating purposes. Molten carbonate fuel cell or MCFC. The advantage of MCFC is that it can use various fuels such as hydrogen, natural gas, propane, diesel, and gasified coal. When natural gas or biogas is used, the conversion from natural gas or biogas to hydrogen is accomplished within the cell. Molten carbonate, salt mixture, immobilized in a porous matrix are used as the electrolyte. Solid oxide fuel cell or SOFC. Phosphoric acid and molten carbonate are highly corrosive, which cause material problems and reduce cell life. A thin layer of solid ceramic material is used as the electrolyte in SOFC, allowing reliable design in high temperatures. They can use the carbon monoxide, hydrogen, and a gasified coal as the fuel. Natural gas can also be formed into hydrogen within cell.
Next are the applications of hydrogen fuel cells. Fuel cell powered cars, bikes, stationary and portable generators, and electronic devices can all use hydrogen as the fuel. With this, fuel cell vehicles fueled by hydrogen is now being introduced to the market by major car companies. In most engineering student competitions, hydrogen cars use the technique of storing hydrogen in a metal hydride solid. Cooling a hydride Cooling a hydride allows absorption of hydrogen while heating it slightly releases hydrogen as a gas. So in this slide, we can see the comparison between hydrogen fuel cell cars and electrical cars powered by lithium-ion batteries. First, the heating value or energy value of a substance is the amount or quantity of heat released during the combustion of a particular amount of that substance. So with this, hydrogen fuel cars have a lower heating value amounting to 120,000 kilojoules per kilogram, while lithium ion batteries have a specific energy of 41,000 kilojoules per kilogram. Next is the system specific energy. So considering an approximate 100 kilogram weight of fuel cells stuck in an automobile, an approximate operating voltage of 0.7 volts, the specific energy for a fuel cell system becomes 1,700 kilojoules per kilogram, while with lithium battery, the system has a specific energy of 5,455 kilojoules per kilogram, considering the total weight of a 1 kilogram current lithium-ion battery containing 840 kilojoules of a electrical energy. So storage is difficult for both hydrogen and lithium batteries. The containers are very heavy compared to the weight of hydrogen and lithium themselves. So for lithium metal, a a safe storage is needed to prevent runaway thermal events leading to combustion. So lastly, the amount of energy that can be stored in a given system or substance is the energy density. The energy density of a commercial lithium-ion battery is currently about 2,500 kilojoules per liter, and for comparison, the energy density of a gasoline is about 32,000 kilojoules per liter. So this discussion only considers the storage of hydrogen as a compressed gas, since this method is normally used for the fuel cell automobiles. Now we'll move on to the challenges related to hydrogen production. So production, storage, transportation, refueling, and use of hydrogen present a number of technical, economical, and practical problems. First, metal hydrides are not as commercially ready technologies as compressed hydrogen gas. Its highest risk elements for manufacturing readiness were process capability, facilities, and manufacturing planning. Second, compressed hydrogen fuel tanks are now made of carbon fiber composites or carbon fiber and metal alloy composites. Hence, manufacturing of hydrogen tanks requires energy input. Third, storing hydrogen in liquid form in cryogenic temperatures. So, hydrogen can be physically stored as either a gas or a liquid. And the storage of hydrogen as a liquid requires cryogenic temperatures because the boiling point of hydrogen at 1 atmosphere pressure is negative 252.8 degrees Celsius. And lastly, mining and manufacturing processes of batteries are energy intensive. Also, the disposal of batteries has some environmental risk like ecotoxicity and water pollution. As batteries corrode, their chemicals soak into soil and can contaminate groundwater and surface water. So lastly, many studies are being conducted to address the issues of hydrogen production and distribution. So here are the long-term solution to hydrogen distribution. So first, to power hydrogen fuel buses, automobiles, bikes, and equipment, a number of hydrogen refueling stations are now available. Japan has 91 public hydrogen refueling stations. Germany has 45 and another 11 private stations, and USA has 40. So with the total number of 328 refueling stations in the world, Germany is planning to increase the number to 400 by 2023. Next, so a possible long-term solution to hydrogen distribution structure is the formation of national hydrogen pipelines. So this can only be justified economically with a widespread use of fuel cell automobiles on the street. Also, for locations without any hydrogen fuel infrastructure or fueling stations, local electrolysis and reformation based technologies can be used. So lastly, battery, hybrid, and fuel cell technologies are all expected to play important roles in future automobile market, as evidenced by the fact that major automobile companies continue to invest in all these technologies. So a widespread hydrogen distribution structure and a large scale renewable based hydrogen production are essential if fuel cell automobiles will have a good share among other competing technologies.